Today in section 2.6 we're moving away from graphing and into something that's more algorithmic, more actually doing computations and following step by steps. When you have an algorithm, usually you have a series of steps to follow. We're going to be combining and finding compositions of functions. Now these are not the same thing, okay? We're going to start with combining functions and then we're going to look at composition of function, which is a specific way to combine functions. Anytime you're combining two or more functions anyway, with whatever way you want to do it, you have to remember to pay attention to any limits on the domain of the original functions. If you have limits on your domain, like for those parent functions, some of our domains have limits of 0. Some of them are all real numbers. If you have limits on the domain of the original functions, that is going to affect the domain of the function you end up with when you combine. So, first step here, always find the domain before you simplify and combine the functions and simplify. So there's a first step that you need to pay attention to. Always find the domain first. Now, when you're finding restricted domains, you're looking for values that would cause the function to be undefined. Division by 0 is one way the function is undefined, right? Or have an imaginary output. So division by 0, let's just do x over 0. That's how a function would be undefined. Or have an imaginary output. That's going to be square root of a negative underneath a radical. Square root of a negative. That's an imaginary output. These function values don't show up on our real number coordinate plane. Undefined doesn't exist. Imaginary, we are graphing on real xy axes, so that's not going to show up there. Now there are two basic causes for these domain restrictions to happen. One of them is if you have a square root right there. Square root of a negative is my imaginary number. So if I have square root x, x has to be greater than or equal to 0. X has to be positive or it has to be 0, or you're going to have an imaginary output. If you have a rational function means that you have variables in your denominator. Variables in the denominator set up the situation where it could be undefined. So for example, if I have 5 over x minus 2, if I plug in x equals 2, then I have 5 over 2 minus 2, which is 5 over 0, which is undefined. That doesn't work. So my domain would be everything but 2. So my domain would be all real numbers, negative infinity up to 2, or 2 to positive infinity, but I've got to leave that 2 out. My domain cannot include 2. So example. Okay, so those are our common causes for domain restrictions. So let's practice. Now, I want you to get used to using what you already know. Use all your knowledge that you've already got. I want you to start by thinking what kind of function you have. You may not be able to answer that question, but if you can, think about what type of function it is. Think about what the graph looks like. Then you can worry about restrictions on its domain. 3 times x minus 4. Well, if I distribute that 3 in, I've got 3x minus 12. What type of function is that? Hopefully you recognize that since it's just x, that is a linear function. What's my domain for a linear function? Well, my domain is all real numbers. Now might be a really good time to grab your parent function page if you don't have that. So there are no restrictions. On a typical linear function, not constant, not a vertical line, there's no restrictions. How about this second one, g of x? Well, I've got that x squared there. That tells me that this is quadratic. Think about your graph for your quadratic function. You've got that parabola that gets moved around. That's where my parent sits. What's the domain for my quadratic function? Use your parent function sheet if you need it. Pause this and go grab it. All real numbers, so I've got no restrictions again. What about this one? What type of function is this? Now, if you've got your parent function sheet, this is one of those 3 at the bottom of that original parent function sheet that I told you we don't have to worry about till Unit 3 or 4. But we're going to talk about it now. Right here, rational functions. Anytime I have a variable in the denominator, that's what we call our rational function. If you have that parent function sheet, you can see that my rational function has places where I have what we call asymptotes. We've got that x in the denominator, the variable in the denominator. Denominator is down, it's the bottom. Division by 0 is undefined. So I need to take a look at that denominator and see what makes this 0. I have to exclude that. Whatever causes that denominator to be 0, I have to kick that value out. So if I solve for x here, I add 5 to both sides, x equals 5, I have to exclude that value. So my domain is going to be everything but 5. X can't be 5. In terms of intervals, negative infinity to 5 or 5 to positive infinity. Later on, we're going to do what we call set builder notation. I'll give you an introduction to it right now, but you don't need to stress about it. My domain, fancy braces, all values x such that x is not 5. That's set builder notation. This is interval notation. All right, let's look at another one. What type of function is this? Well, you might have a couple of answers for me because it's kind of involved, right? We've got a linear here, we've got quadratic here, but overall, this is going to be rational because we have variables in our denominator. Now, I want you to think about this with me. Our numerator is x plus 7. Does it matter what number is in my numerator? Positive, negative, 0? 0 over anything is just 0. So this numerator can be anything it wants to be. Doesn't matter. What I'm interested in is this denominator. My denominator can't be 0 because division by 0 is undefined. So I need to figure out what would cause that denominator to be 0. So I've got x squared plus 6x plus 8. What's going to make that 0? I need to kick that out. Now this is quadratic, it's squared. How do I solve quadratic? Well, I want to factor it if I can. So that's what I'm going to try to do. X times x would give me x squared. My signs are going to be the same. They're both going to be positive, so plus and plus. What are factors of 8 that give me 6 as a sum? So 8 is 1 times 8 or 2 times 4. 2 plus 4 is 6, so those are going to be my factors. Then zero factor property says if this times that is 0, then one of those has to be equal to 0 or both. So we're going to set that equal to 0 to see what would make that happen. So what I find out is if I plug in -2 for x or I plug in -4 for x, I will get a 0 in my denominator and my function will be undefined. So those values have to be excluded from my domain. Now, this is where my set builder notation makes a lot of sense. Set builder notation, I would be able to say, okay, my domain is going to be all values of x such that x is not -4 or -2. That's my domain. but I don't think my math lab lets you get there yet. So here's what we're going to do. We're going to say, okay, my domain can be anything except -4 and -2. Can't be -2, can't be -4. It can be all of these other things. So if you need to do interval notation, your intervals are, for your domain, your intervals are from -∞ to -4, or -4 to -2, or -2 to +∞. That's how you write your domain in interval notation. Sketching a quick number line really helps, so consider that. This is my interval notation. This is my set builder notation. Two different ways to write the domain. Okay, so let's switch gears a little bit. What type of function is this? Hopefully at this point you recognize that this is a square root function. Now remember, we said that our danger with square roots are that we could end up with an imaginary output, imaginary value. 0 is fine. Square root of 0 is not a problem. Square root of a positive number is not a problem. Square root of negatives, those give me problems because that's my imaginary numbers. So I need to set whatever's going on underneath my radical as greater than or equal to 0. So that's what I'm going to do here. I'm going to pull this out, and I'm going to say this needs to be greater than or equal to 0. So what does that give me for restrictions on my domain? Well, if I solve that, I add 2 to both sides. I have x values greater than or equal to 2. That needs to be my domain. Now that's easy. X values greater than or equal to 2. I can think of that on a number line again. Greater than or equal to 2 looks like this, or I can fill it in there. As an interval, my domain is from 2 to +∞. Okay, let's look at the next one. Again with a numerator, we don't care what's going on in the numerator. 5x, that can be 0, it can be negative, it can be positive, not a problem. Now we've got a denominator. We've got this rational function with this radical bit in my denominator. It's a rational function with a square root in the denominator. So we already said that we've got to limit this so it's not negative. Since it's in the denominator, also cannot be 0. So I've got to take this radicand, that value underneath the radical, and this time I have to say it has to just be positive. Can't be 0, can't be or equal to, because I'm in the denominator, and division by 0 is undefined. So now I've got x values greater than 2, not greater than or equal to. So my domain is 2 to infinity, where 2 is not included. You see the difference between those two. If it's just a square root floating out there in space, 0 is fine. Square root of 0 is 0. But if that square root is my denominator, division by 0 is undefined, 0 doesn't work now. It has to be greater than 0. We need positive values only. Okay, last one. Rational function. Again with a square root. This time though, my square root's in my numerator. We said up here, numerator can be anything, numerator can be anything, which is true, but we don't want imaginary numbers still. So even though this is in our numerator, we don't want, we want no imaginary numbers. So I have to say, okay, x minus 2, can this be 0? Numerator can be 0, so greater than or equal to 0. So x has to be greater than or equal to 2. We got that figured out. But wait, there's more. We also have a rational, so it's denominator. My denominator, I need to see what would make my denominator 0. X minus 5, what makes that 0, because we've got to exclude that. If x is 5, we have 0 in our denominator. So we've got a restriction from our numerator and a restriction from our denominator. In order to put those together and make sense of those, we need a number line. I'm going to put a 2 on there, and I'm going to put a 5 on there. Now I know that I can't use 5, so that's going to be an open circle. And I know that my x values have to be greater than or equal to 2. So I'm moving from 2 to the right, but I gotta jump over 5 because I have to exclude 5. So this picture tells me that my domain is from 2 to 5. 2 gets to be included, 5 is not, or 5 to positive infinity. Okay, so that's looking at domain. We have to think about restrictions on our domain before we can combine our functions. All right, how do we combine functions? Well, really, this is the easy part. For basic algebraic operations, sum, difference, product, quotient. Add, subtract, multiply, divide. Those are our 4 basic functions, ways to to combine our functions. This literally means I'm going to take the first function and I'm going to add to the second, so I combine like terms there. For this one, I take my first function, I subtract the second function. Here I'm multiplying the 2 things together. And here I'm dividing. Now, these first three, are going to have the same domains as the original functions. So whatever restrictions I had on the original functions, I have those same restrictions on my combined function. This one though, because of that denominator bit, I have introduced a function into my denominator, automatically set it up that I've got this rational function going on. I may have additional new restrictions on my domain. So I've got to watch for that, okay? All right, let's start with some really basic functions. Just for an example, if I say f of x is x plus 3, g of x is 2x minus 5, these are both linear functions, they're lines. My domain for linear functions, all real numbers. So if I'm going to do a sum, if I'm going to do f plus g of x, that literally means I take f of x, x plus 3, and I add g of x, 2x minus 5. So I'm going to add those like terms. X and 2x is 3x, 3 minus 5 is a negative 2. If I wanted to do x minus g, f minus g of x, I've got that first function f of x minus the second function g of x. Well, in this case, I need to make sure I distribute that negative. So that's a negative 2x plus 5. That gets me x, and negative 2 is a negative x. 3 plus 5 is 8. So you see what I'm doing there. We are performing the arithmetic on the functions. All right, let's do a few more practice problems. I've defined 2 new functions for you. I've got f of x here, g of x here. This is a square root function. Square root function has a limit on the domain. My domain for my square root function is 0 to infinity. What type of function is this? Quadratic. Domain is all real numbers. That means that for minus, plus, and multiply, my restriction on my domain is going to be that 0 to infinity. It only is going to work, it's going to give me real solutions if I have a domain value that is 0 or to infinity. Domain of each function. Right here, if I'm going to add, subtract, or multiply, my domain is 0 to infinity. If I need to divide, I have to check for new restrictions. It's going to depend on which function goes to the denominator. So if my domain of my functions, add, subtract, multiply, it's going to be the domain, the restriction on the domain of the original. But if I need to divide, I've got to look for new restrictions. So on number 5, we'll have to think about new restrictions. All right, f minus g of x. F of x is 3 square root x minus 2. I need to subtract from that g of x. Notice my use of parentheses. That is super important. 3 square root x minus 2 minus x squared minus 5. And I want to combine any like terms and put it in order with the largest exponent first. So my largest exponent is that negative x squared. Then I've got a positive 3 square root x. Negative 2 and negative 5 is negative 7. So I combine those like terms. All right, f plus g of 4. I've got two things going on here. I'm adding the two functions together, and anywhere I have an x, I'm replacing it with a 4. So I've got f of 4 plus g of 4. So let's do that. F of 4 is going to be 3 square root 4 minus 2 plus g of 4 is going to be 4 squared plus 5. Well, what's the square root of 4? Square root of 4 is 2, right? So that is 3 times 2, which is 6, minus 2. And then I'm adding to that 4 squared is 16 plus 5. Well, 16 and 5 is 21, plus 6 is 27, minus 2 gets me to 25. All right, next up, we've got f times g of 0. So that is f of 0 times g of 0. All right. Looking at our functions, f of 0 is 3 square root 0 minus 2, and I need to multiply that times g of 0. 0 squared plus 5. Well, square root of 0 is 0, and anything times 0 is 0, so this is a negative 2. 0 plus 5 is 5, which gives me a negative 10. And then finally, we have to do f of 9 divided by g of 9. Well, f of 9, that's going to be 3 square root 9 minus 2. G of 9 is 9 squared plus 5. And here we go. We've got square root of 9 is 3, so that's 3 times 3 minus 2. 9 squared is 81. So I have 9 minus 2 is 7 over 86. All right. Excellent. Let's take a look at our final way to combine functions. Now, we're going to combine these functions using compositions of functions. Now, when we did multiplication here, we can just write it side by side. We can do a dot. We do not want to do an open circle because an open circle is the symbol for composition. Composition of function means that when the output of one function is the input of the next. Now, we do composition of functions all the time. When you go out to eat, you take the cost of your meal and they plug that into a calculation and get tax, and then they take that answer and add it in and to get the final total of your meal. When you do pay taxes, income taxes and Social Security taxes, they calculate those off of your hours worked, your gross wages, whatever, however you're paid, salary or wage, and then they take that and plug it in. Order matters when I am doing composition of function. It's not the same as adding, subtracting, multiplying, or dividing. Order does matter. For example, f composite g is not the same thing as g composite f. F composite g of x means I'm taking this and plugging it into whatever function is named first. So again, what's named second gets plugged in to what is named first. Order matters with composition of function. This is read f composite g of x. This one is red, G composite f of x. Okay, let's do some practice on this, and then we will be done with section 2.6. I have defined 3 different functions for you: f of x, g of x, and h of x. Square root, linear, quadratic. We're going to find first f composite g of x, which means I'm taking g of x and I'm plugging it into that original function f. F function is the big function. G of x gets plugged in inside. Here's g of x. So my f of x function is square root of. Instead of that x, I'm going to take the g of x function and I'm going to plug it in. I took out the x in the f function. I replaced it with the g of x function. Now, in this case, there is nothing else to do there. Can't simplify that, so I'm done. We're going to skip down to number 3 and do it in the other order. G composite f of x. So I take that f of x function and I plug it in to g this time. That order matters. So my g function is right here. 2 times x minus 1. That's g. F of x is square root x. So I can see that that gives me 2 square roots of x minus 1, which is not the same thing as when I did the other order. Now let's show that this is true with values. F composite g of 5, so we're going to find g of 5 and plug that into f. So let's do that. Let's find g of 5, order matters. 2 times 5 minus 1, 10 minus 1 is 9. G of 5 is 9. Now I'm going to take that g of 5, which is 9, and I'm going to plug that into f. So then I do f of 9. F is square root of, that gives me 3. Down here, g of f of 5. So I'm going to find f of 5 first. F of 5, right there. Square root 5 can't be simplified. I'm going to plug that into my g function. G function is 2x, so now it's 2 square root 5 minus 1. That's it, we're done. Now let's show that it is true by using this value. F composite g of x, f composite g of x is square root of 2x minus 1. If I do f composite g of 5, which is what I was asked here, square root of 2 times 5 minus 1, square root of 10 minus 1 is square root 9, that's 3. Right here, this is g composite f of x. So if I do g composite f of 5, right here, 2 times square root 5 minus 1, and that's what I got. So we worked it 2 different ways to prove to you that it was going to work. All right, let's do all 3 of them in composition. Order matters. We start at the end. We're going to start with f of 9. F of 9 would be square root 9, which is 3. I'm going to take that and I'm going to plug it into g. So I've got g of 3, 2 times 3 minus 1. I'm looking at the functions up above. 2 times 3 is 6 minus 1 is 5. And I'm going to plug that into h. So h of 5 is 5 squared. That gives me 25. Alright, so output of one function is the input of another. Now let's look at functions a little differently, keeping that order of operations bit in mind. We are going to define composites with sets. F is the set of 3 ordered pairs, G is the set of 3 ordered pairs. Go in order. So number 6, F composite G of 1. Well, what is G of 1? G of 1 is 4 right there. G of 1 is 4. So that's my output. I take that as the input of the second function. So now I need to do f of 4. So I go to my f function where x is 4, y is 9. That's my answer. Again, remember you can pause, stop, go back. Let's start with g of 2. Go to my g function. G of 2 is 5. Plug that into the f function so that I need to find f of 5. Function f of 5, the y value is 10, and that's my answer. Alright, last one here, and then we're done. G of 3, so that's what I'm looking for first. Go to my g function. G of 3, the y value, the function value is 6. Plug that into the f function. F of 6 is, and I look at my f function, and there is no x value 6 here. That does not exist. That is outside the domain. Doesn't work. All right. Excellent. We'll see you again for 2-7.